Hey folks, Nathan here. Today we'll be diving into the world of rocket simulation by starting the creation of a very simple water rocket simulator. It's going to model a rocket flying purely in the vertical axis and flying in ideal conditions. Air resistance will be calculated, but wind and stability will not be. To research this, I looked up a whole bunch of water simulators online, and every single one of them gave a different value for burnout time, max altitude, and flight time. So this indicates to me that we're probably not going to be building anything super accurate, which I'm okay with as long as we're in the right ballpark. So to start things off, we'll be building this simulation in Unity using C#. You can build your simulator in pretty much any language, but I've picked Unity because it's a game engine and gives us a decent rendering engine for some of the longer term goals of the simulator, as well as a variety of other benefits. For the first part though, all our outputs will be in text. So we're using equations provided by the sciencebits.com water-propelled rocket page. I'll note that I was unable to get the same result as their solver that they have on the website, but it's entirely possible that either I've messed something up slightly in my own code, there's a secret source in their code they haven't explained, or that some of the values that I've used for initial conditions don't match what theirs are. So, with all that, let's dive into the code. Okay, here's our code. So everything runs just out of this simulation script. Kick things off our starting variables. These are the ones that we set ourselves. So we have the time step, which is how long in seconds each iteration of the simulation is going to go for. I have the volume of our rocket, the radius, the fuel volume, the fuel density, the pressure of the air that's in the rocket, the nozzle radius, gravity strength, drag coefficient, the dry mass of the rocket, the adiabatic index constant used for the change in pressure simulation, the external air pressure, and the external air density. So these are all set by us at the start of the simulation. So we can see up here in the simulation, we have all those values here. So up is the derived values, so the wet mass and the drag force. So these are calculated right at the start of the simulation. The live conditions, which are the ones that are calculated each iteration and constantly updated. So we have the time, the current mass of the rocket, the current internal pressure of the rocket, the current rate that mass is being ejected from the rocket, the current fuel volume, the current velocity of the rocket, and the current height. So, kick things off, when we hit our spacebar, we calculate our starting conditions. Basically, we set the time to 0, we calculate the wet mass by getting the dry mass and adding the weight of the fuel. We calculate the drag force using the drag equation. Then we just set our initial values, so the pressure is the starting pressure, the velocity is 0, etc, etc, etc. And then we log that stuff there, so when we actually start this up, we'll see that we've done our starting conditions. Say that again, so we do it from scratch. Yep, so we have our wet mass as 0.76 kilograms, the drag force is 0.0048, and yeah, these are going to be used in our live calculations. So next up, when we hit our right arrow, what will happen is it's going to run the simulation as long as the height is above 0. It means we basically run from when the rocket launches to when the rocket comes back down. So each tick of the simulation, we calculate our new parameters and then we log those values. So calculating new parameters here is sort of the weighty bit of the simulation. So we start out by advancing time. We initialize the variables that we're going to need for each tick of the simulation. So we have our change in velocity and the exhaust velocity of the rocket. We have the current mass loss rate, the current mass, which is just the last mass minus the loss rate divided by the time step. Here we just make sure that the current mass is always at least the dry mass, because you can't eject the dry mass from the rocket unless something's gone really wrong, and we only want to simulate rockets that work for now. We calculate the current volume of the fuel remaining. So we just take our current volume, take the current mass minus the dry mass from it, and divide that by the density to get the volume. Calculate the new internal pressure is done with the pressure equation, so we get our pressure, then the adiabatic gas expansion to calculate. That is on the ScienceBits website. Now, depending on whether we're currently accelerating or not, depends on how we calculate our forces. So if we are accelerating, we need to calculate a thrust force, which is going to depend on our nozzle radius squared and the current difference in pressure between the inside and the outside of the rocket. So we get that, calculate everything, throw it in, and we get the current velocity is the current velocity plus the time step in seconds, the rate of change. Otherwise, if we're under gravity, the change in velocity is just minus gravity minus drag. Then we update our height, and there we go. So what we're going to do is jump back into our simulation. We're going to hit the simulate button. Our starting value is there. We can see that we have a whole heap of time steps here. Go back up to the top of these. So speed, height, current mass, and remaining fuel all listed there. You can see now that our fuel's run out, roughly between 0.14 and 0.15 seconds. Now as we go, the speed's going to go down, the height's going to go up because we're currently just going up and getting slowed down by gravity and air pressure. Down at around 1.66, 1.65 to 1.66. We've hit our apogee, our speed goes from positive to negative, and we hit a max height of about 15.5 meters. And we come down, we start coming down real quickly until at 3.2 seconds, it looks like. We crash into the ground with a speed of 26 meters per second, which is not the speed you want your rocket to crash at. And that's the first part of our simulator finished. So all the basic maths in there, and we're getting answers that are in a similar ballpark to what the other simulators are giving us. So I'm pretty content with how it's going. We'll build on it in the future to try and do some fancier stuff with it. But for now, I think it's a reasonable representation of how any water rocket I build will fly. And with that, that's all for today. Catch you later.